Hello to all of you. I am Dr. Deepak Yadav, and we are going to discuss some complex topic of antenna and wave propagation subject. That is one of the important subject of BTech third year. And today we will going to discuss the topic wave propagation, how different wave are traveling from transmitting antenna to receiving antenna by different using different types of channels like ground wave propagation, sky wave, and space wave propagation. So here is our first slide, that is ground wave, space wave, and sky wave propagation. So as we can know that the wave propagation is depending upon the frequency that is going to be used in the transmission and the behavior of the wave that is produced by the different antenna system. As we can see over here, the wave carrying information are generated by the transmitting antenna. Electromagnetic wave radiated by the transmitting antenna is transverse wave, and when electromagnetic wave is produced by the antenna, it travels from transmitter to receiver using following ways. The first part is a part of the wave that is travel along near the surface of the earth, that is known as ground wave or surface wave propagation. Some wave travel directly from the transmitter to the receiving antenna is called space wave propagation. And the third one is when the wave is shooted in the sky directly and that is reflected back by the ionosphere, then that wave propagation is known as sky wave propagation or ionospheric wave propagation. The method by which the radio wave travel in the free space is called the mode propagation. Modes of wave propagation. The energy may reaches the receiving antenna by number of propagation, and these are the propagation that a wave can use, either ground wave propagation, space wave propagation, or sky wave propagation. So on the basis of these propagation methods, the total wave is divided into ground wave, sky wave, and space wave. So what is ground wave propagation? So when the wave are guided along the surface of the earth, just an electromagnetic wave in the guided medium, like the wave travel in the waveguide. In the similar way, when the wave is travel near the surface of the earth and using surface of the earth as one wall of the transmitting media, then we can say that the propagation is known as the ground wave propagation. This propagation exists when the transmitting and the receiving antenna are close to the surface of the earth. So let's suppose if this is the earth and this is the transmitting antenna, the antenna that is going to be transmit the signal, and this is the receiving antenna, the signal that is received by this antenna. So the wave is now reflected back from the surface of the earth and using one of the wall of the medium to receive the receiving place. Then this wave propagation is known as ground wave propagation. Ground wave propagation. So in this case, the ground wave propagation is generally generated by the vertically polarized antenna. The second propagation, this is not very much used currently, but this is one of the way of propagation of the wave. Now the second is the space wave propagation, and this propagation is very much in use in today's scenario, in which a troposphere is used as the medium of the transmission of the electromagnetic waves. And there is two type of wave in this propagation. Like when the wave is transmitting from the transmitting antenna to the receiving antenna, the wave is either going direct from the transmitting antenna to the receiving antenna by using the space between the transmitter and the receiver, or the wave is either reflected back from the ground and go back to the transmitter. So in this way, these two waves are reaches from transmitter to the receiving antenna. So the wave propagation which involves these techniques is known as space wave propagation. And the third propagation is known as the sky wave propagation. So in the case of sky wave propagation, the wave is shooted from the transmitting antenna to the receiving antenna, and the wave is shooted to the ionosphere, and due to the different concentration of electron in the ionosphere, the wave gap reflected back to the receiving antenna and received the signal by the receiving antenna. So this kind of propagation is known as sky wave propagation. So we have three, either ground or space or sky wave propagation. The frequency used in these propagations are up to 2 megahertz. We use ground wave propagation. Ultra high frequency and microwave frequency up to 300 megahertz, space wave propagation, and the frequency range strictly between 2 megahertz to 30 megahertz. We use sky wave propagation. Above 30 megahertz, the sky does not reflect, the ionosphere is not able to reflect the high frequency signal which is greater than 30 megahertz to reflect back to the earth. So the sky wave propagation is limited between these two frequencies. The space wave or tropospheric wave propagation or space wave propagation. So in case of space wave propagation, there are two types of waves, as we already discussed. Either the wave is traveled directly from the transmitter to the receiving antenna, or the wave is going to be reflect from the earth's surface and going back to the receiving antenna. So here we can see the scenario of our earth atmosphere and the earth. This is the earth's surface where is transmitting and receiving antenna. This is troposphere. This is the limit of the troposphere. Up to 15 kilometer we have the troposphere in the earth atmosphere, and from the earth's surface to the height of 50 kilometer our ionosphere is a start. Even in the ionosphere we have multiple layers, that is D, E, F1 and F2 layers. But we are focusing this time for the space wave propagation. So the troposphere is the main region where the propagation exists, space wave propagation exists. So there are two types of wave. The wave is either transmitting from the transmitting antenna to the receiving antenna directly, or by reflected from the ground to the receiving antenna. So the frequency used is very high and ultra high frequency. The signal must be, or the transmitting and receiving antenna must be a line of sight. The transmitter and the receiver must be in the line of sight. So the example of space wave propagation we generally use in TV, radar and FM radios. So multipath wave propagation. So as we discussed already, this is the direct wave propagation and this is the reflective wave propagation. And due to the reflection of the wave can travel much larger path in compared to the direct wave propagation. And due to this process, the reflected wave face a delay. And due to this delay, there is a fading occurs at the receiving antenna. The signal strength get fluctuated very much. So how to tackle with this problem? We can use multipath wave propagation technique to see the electric field variation at the receiving antenna. So there is two type of horizon, optical horizon or radio horizon. Radio horizon is generally much larger, larger than compared to the optical horizon. In case of optical horizon, the two transmitting and receiving antenna must be in the line of sight. So if the earth is curved and your receiving antenna is over here, then the line of sight is like this. So this is the line of sight or optical horizon. So between there to there we can transmit the signal. Or in case of radio horizon, the signal get reflected like this, and so the radio horizon must be a little larger than in compared to the optical horizon. So as we can see, this is the optical horizon and this is the radio horizon, as we can see over here. This is the center of the earth and this is the radius of the earth. This is the height of the transmitting antenna and the height of the receiving antenna. The maximum radio range that the wave used for optical range for line of sight communication, we can derive with the help of this figure. So this is the center of the earth, this is the radius of the earth, all the 3 points. If we have the transmitting antenna having height ht and the receiving antenna having height hr and the distance between the antenna is d, so if we split this distance between two distances, that is d1 from transmitting antenna to the optical horizon and from optical horizon to the receiving antenna, d1 and d2. Now this d, the total distance is made up of d1 and d2. First we calculate d1. Then how we can calculate the d1? By using this triangle, So we have R square. This R, this R is equal to okay, we have to calculate this D1. So then this D1 is equal to this R square, R plus HT whole square minus this R square is equal to D square, is equal to D1 square. So we can see that D1 is equal to, D1 square is equal to HT plus HR, HT plus R whole square minus R square ka root. So as we open this square root, we have HT square plus R square plus 2HER minus HR. So this R square is cancelled out and we have D1 is equal to 2HT into R. Where this HT square gone? Because the height of the antenna is very small in compared to the radius of the earth. The radius of the earth is very large, like in multi-kilometer, like 6,370 kilometer, while the antenna is having the height of few meters, like 20 or 30 meters. So this HT square is very, very less in compared to this radius R. So we can neglect HT square here in compared to 2HT into R. So we have the distance 2HT into R. Similarly, for the D2 distance, same method is used for calculating the D2. So D2 square is equal to HR plus R ka whole square minus small r square. So we have, this is equal to under root 2 HR into R for D2. So the maximum distance between these two is D, that is D is equal to D max, and that is under root 2 HT plus R plus under root 2 HR plus R. So the total distance we have under root 2 common, under root 2 into R common, then we have this, put the value of R equal to this, the radius of the earth 6,370, and on calculating we find D is equal to 3.57, height of the transmitting antenna under root plus height of the receiving antenna under root. This is the maximum distance when a transmitting and receiving antenna can be apart using radio horizon, and it can be approximated to 4 because there is a variation in the temperature, in the day-night merging of the layer. We can approximate this value to up to 4. So the D maximum is equal to 4 times of under root of HT, height of the transmitting antenna and height of the receiving antenna, and the distance is in kilometer. So we have one example for this. Let the height of the transmitting antenna is 225 meter and the receiving antenna is 1 meter. So we have 225 under root 225 under root 1 and 4 times of this. So we have 25 plus 1, 26 times of 4, sorry 15 plus 1, that is 16 times of 4, that is 64 kilometer over here. So we can say that the antenna can transmit up to 64 kilometer. The signal can transmit up to 64 kilometer. Similarly, for the height of the antenna is 16 meter, we can able to transmit the signal up to 76 kilometer. So there are some more examples. The value is in feet, so we can calculate the same distance in miles. And if the transmitting and receiving antenna had the same height, then we have the value like this. In the similar way, we can solve this question as well. Field strength relationship of the transmitting and the receiving wave. So how that wave is going to be like reduce its value, reduce its magnitude when it travels from the transmitter to the receiver. So we have two types of waves. That is a wave that is traveling direct or by the reflection of the wave. So from the image theory, we can assume that the wave is traveling from the toward the receiving antenna by following this straight path. This path length is equal to this path length, because this HR is equal to the height of the receiving antenna is equal to height of the receiving antenna. So we have two triangles. The one triangle is this, where we have R1 is equal to HT minus HR, because this value is HR and this is HT, that is HT minus HR ka whole square plus D square, and the another triangle is R2 HT plus HR whole square into d square, that is r2 square. So by using these two ray paths, we can calculate the electric field strength at the receiving end, and r1 is equal to ht minus hr whole square plus d square. So now take the d as a common, we have this value. Now ht minus hr is very small. Ht minus hr is already very small because this is the difference between the heights of the antenna, and d is very large, the distance between the two antenna, that is, it is in multiple kilometers. So the term this ht minus hr whole square by d square is very small. So we can use the binomial theorem or binomial approximation to approximate the value, and we can put this 1 by 2 in the multiplication over here, that is 1 by 2 for this value, and similar for this value. So we have d is equal to, this r1 is equal to d plus ht minus hr whole square by 2d. This is equal to range r1. Similarly, we can calculate range r2. Here in this case we have ht plus hr whole square. Same binomial theorem is applied because ht plus hr is still very less in compared to the distance between the transmitting and receiving antenna. So we have 1 by 2 in multiplication, and r2 is equal to this. So the total path difference between the ray 1 and the ray 2, that is reflected from the ground, we have r2 minus r1. So ht plus hr whole square by 2d minus ht minus hr whole square by 2d, that is 4 ht hr by 2d, that is equal to 2 ht into hr. Now the path difference is actually the phase difference that is faced by the different wave, and we can calculate the phase difference is equal to 2 by lambda times of path difference, then 2 by lambda times of 2 ht hr by d. So we have this much radian value, that is that the two wave can going to be phased when it is going through direct or by reflection from the ground. And there is another beta term, that is another phase difference added in the reflected wave due to the reflection from the ground. When the wave is reflected from the ground, it is supposed to have a phase difference of 180 degree. So this 180 degree is also added in this alpha. So the total phase difference delta is equal to alpha plus 180 degree. So if we put the electric field equation in terms of the field radiated and received by the transmitting antenna. So this is the way, this is the field that is received by the receiving antenna by direct propagation, and this is ER is the magnitude of the field that is received by the receiving antenna when the wave is going to be reflect from the surface of the earth, and due to this factor, due to this delay, there is a change in the amplitude of ER. So let's suppose ED is equal to ER is equal to ES, that is received. So we can find that E is equal to ES 1 plus e to the power j alpha plus 180 degree. On solving this complex e to the power values, we have cos alpha plus minus j sin alpha plus 180 degree. On solving this, we get the amplitude of E is equal to under root of 1 minus cos alpha whole square plus sin alpha whole square. By opening the cos square alpha whole square and on solving by using half angle formula, we have the electric field strength that is received is equal to E naught by D under root of 4 sin square alpha by 2, where alpha is the path difference, where alpha is the phase difference due to the path difference between the two waves, that is direct wave or reflected wave. E naught is the strength that is radiated by the transmitting antenna. So we have the path by putting the value of this alpha, we have the electric field strength in terms of electric field strength that is radiated by the transmitting antenna, that is E is equal to 2 E naught by D sine of 2 pi HTHR by lambda D. And on solving, the field E at the receiver end is equal to this, where E is the field strength of the direct wave, height of the antenna, height of the receiving antenna, and distance between two antenna. Now again, the sign, this HT into HR is very small in compared to the distance between the antenna. So this angle is very small, the angle of the sine is very small. So we have the identity sine theta is equal to theta if theta is very, very small. So in case of this, where theta is very small, we can find this, we can able to remove this sine term over here. So this is equal to this only, and then putting this value, we have electric field that is received is equal to this times of the electric field that is transmitted by the transmitting antenna. So by putting the values, approximate values of HT, HR and distance between the antenna, we can approximate, and for the half wave dipole specifically, we have E naught is equal to 2 to 1.4 under root P, where under root P is the power in kilowatt that is transmitted. So E naught is equal to 7 times of under root P. And for the half wave dipole, we have the electric field strength is equal to this 88 under root P. P is the power transmitted, HT height of the transmitting antenna, receiving antenna, by distance between the antenna, and the value is in volt per meter. So thank you for this lecture. In this lecture, we will discuss completely about the space wave propagation. In the another class, we will discuss about the sky wave propagation.